Welcome to this NPTEL course on topological phases of matter. My name is Tanmay Das and I am an associate professor in the Department of Physics at Indian Institute of Science. So in this NPTEL course, I want to introduce you to one of the most exciting and actively pursued field of quantum condensed matter physics for over the last 2 decades. One of the most fascinating facts about this topic is that this topic used to be thought of as mathematically abstract, but now, such as manifolds, curvatures and topology, these things has now been realized in real materials. So I have designed this course to provide you a holistic and intuitive understanding of the topological phases of matter, starting from the mathematical background, then moving towards the physical implications and measurable quantities. I will begin with the mathematical foundations of geometry and topology, and some of these mathematical foundations actually stem from the general theory of relativity, where physicists figure out how to write physics laws on curved space. And on curved space, you cannot define a uniform reference frame. So what does is that one would define a reference of frame locally, and then nearby reference of frame has to be connected through something called connections. So this idea gave rise to topology, and then that topology ended up in quantum mechanics in this way. So in quantum mechanics, we deal with wave functions, and wave functions are also written in a basis, such as the energy eigenbasis of a Hamiltonian, and the bases are very analogous to reference frame. Energy basis of Hamiltonian becomes position or momentum dependent in certain materials, and if this happens, then also we have to define connections to relate nearby bases, and that connection is called Berry connections. And this is how the Berry phase, winding number, Chern number all arises. And based on this Chern number and winding number, we derive many topological properties that we will study in depth in this course. So at this point, one may wonder, how does such beautiful mathematical concepts give rise to physical phenomena? And I can start with a real life example, such as the reverse swing of a cricket ball. So that phenomena is actually governed by topology, in which the cricket ball gains some transverse velocity as we change its topology. And then we will study many real examples of condensed matter system, such as quantum Hall effect, topological insulators in all 3 dimensions, and their symmetry classifications, the connections between vortex and skyrmions in spin systems and classical systems, with winding number and Chern number in quantum mechanics. And also I look into several prototypical models, such as Schur-Schrieffer-Heeger model, Key-types superconducting chain, Ken-Millet model, Halden's model. There are many more models in three-dimensional topological insulators. And then I will also talk about various topological semimetals like Dirac, Weil and Noether-Line semimetals and so on. And then we will move on to study bulk boundary correspondence, age states and the related phenomena, and even more modern topics such as quantum geometry, quantum metric, flat band topology and compact orbitals. All these things also will be studied. After that, we will also discuss about how all these fascinating properties can be measured. And in that context, we will of course study the quantum Hall effect, anti-localizations, negative magnetization resistance, and Berry curvature dipole, non-linear optical properties, and a few other topics which are very modern and novel. So that sums up the topics that I am going to cover. Who will benefit from this course? So this course will be useful for advanced undergraduate students, master students, PhD students, all learners and researchers who are interested in quantum condensed matter, both theory and experiments. To follow this course comfortably, you should have the basic knowledge of quantum mechanics 1, mathematical methods in physics, and condensed matter physics 1. However, I will try to go through the course in a simple and motivated way, such that those who have taken this course will be able to build on their knowledge and understanding for their more advanced studies. I hope this course will give you a solid foundation and enthusiasm to explore this subject. I warmly welcome you to join this exciting journey to the world of topological phases of matter. Thank you and welcome on board for this course.